Hi guys, in this video I am going to speak about odors. Variety of odors, flavors, fragrances, stink, pungent and all those odors. How does transducer help us in recognizing those odors, and also how does it help in discriminating one smell from other, one odor from other odor? That's the topic for this video. Let's get into it. Theory of odor is presumed to depend upon two parameters. First one is docking of molecule, and second one is energies of molecules. But as per my presumption, packing efficiency should also be considered. Would explain as the story moves on. So let's understand docking first. In case of docking, what happens is various molecules generating various odors have different structures. Now, owing to it having different structures, it fit into the cavities or the sites present in olfactory nerves, which are present on inner upper part of our nasal cavity based on lock and key mechanism, which I have explained earlier. Now, since they fit into different cavities, so they produce different responses. That obviously becomes very easy for transducers to differentiate one odor from other. My specialty has been in chirality, so I've got to pick up chiral molecules also. So in case of chiral molecules, both structures, if you see, they are the same. Molecular formula is the same, structural formula is the same, only there is difference in spatial arrangement. Now, since the spatial arrangements are different, so these enantiomers, R and S, DL, plus minus, whatever you call it as, these enantiomers fit into different sites. Now, since they fit into different sites, so obviously responses are different for transducers, hence smells different. Let's pick up caravan. In case of caravan, the R isomer smells of pudina or spearmint, whereas S isomer smells of ajwain, which we call it as caraway. But hold on, this theory is not foolproof, because there are many enantiomers which have same odor in spite of having different spatial arrangement. Alright, how do I explain that? Would be explaining that a bit later. Alright, let's right now pick up energies of molecule. How energies of molecule are discriminating factor for transducers. Now, when we talk in terms of energies, we have got to go back to our school or colleges where we had studied about monoatomic molecule, diatomic molecule, rigid, diatomic molecule non-rigid, and polyatomic molecules degree of freedom. Now, we know, just to recap what we had studied already, monoatomic molecules have 3 degrees of freedom, 3 translational motions, that is in X, Y and Z direction. Alright, so it has 3 degrees of freedom, which we call it as DOF, DOF. Whereas when we take rigid diatomic molecule, it has 5 degrees of freedom. Now, 5 degrees, when we say 3 degrees, when we say 5 degrees, definitely the energies, when it has got 5 degrees of freedom, has much more than 3 degrees of freedom, or diatomic would be having more energy, kinetic energy, than monoatomic. And why does it have 5 degrees of freedom? It's because it has 3 translational motions. Along with that, it also has 2 rotational motions. Alright, then when we come to diatomic non-rigid molecule, it has 7 degrees of freedom. And why 7 degrees of freedom? Because it has 3 translational, 2 rotational and 2 vibrationals. Alright, so it has got 7 degrees of freedom. This gives you a rough idea about energies. So obviously when we are talking in terms of polyatomic molecule, they will have lots of energy. This gives you a rough idea about energies of molecule, right? Let's try and understand kinetic energies of molecules in more depth. Now initially we have monoatomics. Now in case of monoatomics, there are 3 DOFs which I already have explained. 3 translational motions. Every motion has half kBt. So what we find here is it comes to 3 into half kBt, that comes to 3 by 2 kBt. The kinetic energy for monoatomics. For diatomics, we have two types of diatomics. One is rigid, the other one is non-rigid. In case of rigid, we have 5 DOF. It's mentioned which are those 5 DOFs. So 5 multiplied by half kBt comes to 5 by 2 kBt. Then for diatomic non-rigid, we have 7 DOFs and those are mentioned over here. So it comes to 7 by 2 kBt. I need to mention here that in case of rigid, there are these 3 examples which I have quoted. There are multiple of those examples, but I have quoted just these 3. And in case of non-rigid diatomic, carbon monoxide is the example. Alright, so we find how DOF is much greater in case of non-rigid because it has additional vibrational motion along with translational and rotational motion. Coming to polyatomics, now here I have chosen H2S, hydrogen sulfide at high temperature and hydrogen sulfide at ambient temperature have 2 different DOFs. For high temperature, it comes to 9 DOF. That's owing to additional 3 vibrational along with 3 translational and 3 rotational motion. So it comes to 9 by 2 kBt. Whereas in case of ambient, there is no vibrational motion, owing to which it comes to 6 and it comes to 6 by 2. The kinetic energy comes to 6 by 2 kBts. So these are all the kinetic energies that we saw. I have been involving kBt. Kb is Boltzmann's constant, value of which is 1.38 into 10 raised to minus 23 joules per mole, and T is the temperature at which the atom or molecule is existing, and ambient temperature is 298.15 K. These are all the energies that we get. Now need not forget that this energy is again further to be multiplied with temperature in Kelvin. Now let's talk in terms of ambient temperature. In case of ambient temperature, we already have seen the ambient temperature is 298.15 K. All these values we have got to multiply it with say 298 or say approximately 300 times. We multiply these values 300 times to get the energy possessed by monoatomic or diatomic molecules. Now suppose we are in winter. So if we are in winter, the temperature definitely would be much below the ambient temperature. So we have got to multiply this, all these values we have got to multiply with temperature much lesser than 300 K. And if we are in summer, then we have got to multiply these values with temperature much higher than 300 K. What does this imply? This implies that the energy possessed by atoms or molecules, odor producing atoms or molecules, would be much lesser in winter and much higher in summer, owing to which that's what we experience. Any odor producing atoms or molecules, we are less sensitive to it during winter and more sensitive to it during summer. And why is that so? That's because the energy is directly proportional to temperature. More the temperature, more the flavor, fragrance, stink or whatever. And less the temperature, less the stink, less the flavor, less the fragrance. Alright, so that's how it works. Alright, something interesting. Now, this is just to give you an idea about relationship of joules and temperature. 4.18 joules increases temperature of 1 gram of water by 1 degree Celsius. We already have seen energy possessed per mole of atom or molecules here. Alright. Now, obviously, that has to be also multiplied with temperature, which I have already explained. Now, if I am interested in finding out per atom or per molecule, then obviously this has to be divided by Avogadro's number. Why? Because we know 1 mole corresponds to 6.022 into 10 raised to 23 molecules. So for 1 molecule, so 1 mole corresponds to these many molecules. So if I want to find out for 1 molecule, so that value whatever we got for 1 mole has to be divided by this parameter, Avogadro's number. Alright, so Ke divided by this. So ultimately what happens? The kinetic energy would be of the order of approximately 10 raised to minus 46 to 10 raised to minus 43 joules per molecule now. Alright, now you can compare this with this to just to understand the temperature rise. Alright, so at 4.18 joules per degree rise temperature of water, whereas what energy these molecules possesses of this order. Alright, just to give you an idea about temperature rise in our nostril when aroma producing atoms or molecules strikes the sides of our nostrils. Alright. So in terms of energy, the matter appears a bit simplified. Why simplified? Because we know that if we check out this structure and we check out that structure, there has to be something different in them. That's why they are different molecules. Alright, could be bond, could be number of bonds, could be atoms present in those molecules, or rather elements present in those molecules could be different. Their structure would be different, owing to which these molecules would be having different internal energies. So having different internal energies, so these molecules, when they enter into our sites of olfactory nerves, they give different energy to transducers to be transduced in different responses. Alright, so discriminating odor of this molecule from odor of that molecule. Now mind you, I am talking about only odor producing molecules, or we are in terms of aroma. Alright, so that explains about energy. Hope this video was informative. In my next video, I would be touching upon packing efficiency. These are my feelings about molecules being packed in the site. Let's see what I've got to say in my incoming video on packing efficiency. See you then.